Okay, let's continue our discussion about closed sets. So last time we concluded by proving the first part of theorem 17.5, which says that an element is in the closure if and only if every neighborhood of X intersects A. And so the second part actually just follows straight away. And remember, it's useful quite often to do things in terms of a basis, because quite often basis elements are easier to deal with. So it seems weaker, but it's not. X is in the closure of A if and only if every basis element containing X intersects A. Well, given 1, 2 follows straight away, because if X is in the closure of A, then every open set of X, any open set containing X intersects A, or basis elements are themselves open sets. So that part's good. So what happens if what about going the other way? What happens if every basis element containing X intersects A? Well, then we have, so does every open set containing X, right? Because if since an open set will then contain a basis element which will contain X just by the definition of basis. So 2 seems weaker than 1, but actually it's exactly the same thing. Okay. So let's do some examples. So here are 6 subsets of the real number line. Let's figure out what the closure of A is. Each of those 6 are. What do you reckon, Will? You're the only one here.
Closed interval from 0 to 1.
Yep, exactly right. Closure of B. Well, it's going to include B. What extra point else is going to be there?
You only need 1 more point to close that?
Yep, 1 more point will close that.
Is it 0?
Yeah, it's 0.
Why don't we need
Because think about it.
all the stuff in between?
Well, let's think about it. Let's take 0. And let's think about just any neighborhood containing 0. Okay, so it's going to be 0. So it's going to be something like minus delta to epsilon, right? And so all for n greater than 1 on epsilon, those elements are going to be in there. So that's infinitely. So there exists a capital N. Oh no, yeah. So all of those will be in that.
Okay, so if you take a...
Oh, in fact, all you've got to do is actually say that it intersects with B. What? So hang on, I'm thinking more.
I see 0. So the points that are in between the reciprocals, then you'd have to just pick something small enough.
Right. So between a quarter and a fifth, for example, the distance between there is a 20th.
Pick like a 30th for your length of your neighborhood.
Exactly, between there, and then it won't meet there. So that indeed is the case. What about C? So So we have to include C itself. So 0 and 1, 2. What else is going to be in the closure?
1 and 2 themselves.
Yep, exactly. Right, because any neighborhood containing 1 is going to intersect with C. Same with 2, and same with 0, right? Because 0 is itself in there. About the closure of the rationals.
They're dense in R, so you have to go through the R.
Exactly right. Yep. So you know that from your previous knowledge that any real number, you take any neighborhood of a real number, and it's going to contain a rational number. Closure of Z. Yeah, it's just Z, right? Because any non-integer, you can make a small enough. So for example, 1 1/4, you make the interval 1/8 around that, and it won't intersect the integers. And then finally, the positive reals.
0.
Yeah, we'd have to just throw in 0 to there. Okay, so you got a good idea of what the closure is. Okay, so here's another important concept, the next important concept. The idea of the limit point. Let A be a subset of our topological space, and let's say we have some X. And we say X is a limit point of A if every neighborhood of X intersects A in some point other than X itself. So X, i.e. X is a limit point if it belongs to the closure of A minus X. So that means it may or may not lie in A. So let's go back to this example here. So what are our limit points? What about this one here? So if we take any number away from that interval and then look at its closure, what are we going to get?
So everything's a limit point?
Everything's a limit point, yeah.
Everything in the closure.
All the limit points. All right. So let me do it this way. What about for this one here?
It's the same thing, B closure instead of limit points.
No, actually not. It's not. Because remember, so let's have a look at some sequence. You know, like so we have 1, 1/2, 1/3, 1/4, and we got 0, right, at the end. Now, 0 is a limit point, right? Because what? If every neighborhood of X intersects A in some point other than X itself. So that's true of 0, right? Because every neighborhood of 0 meets someone in B.
Then nothing else is a limit point?
And nothing else is a limit point. So for example, take 1/4. Again, we can take a small enough interval, and the only element of B that's in it is 1/4 of itself. So 1/4 is not a limit point in that situation. Okay, so hopefully, what about C? Right, 0 is not a limit point because if we take a small enough neighborhood of 0, say minus a half to a half, the only element of C in there is 0, so that's not going to be, but
that whole interval should be
exactly 1, 2 will be limit points. What about this guy here? What are the limit points of Q?
any real number.
Yep, any real number, exactly, because take an interval and it's going to be a rational in there. This one here, Z. Yep. Empty set here, and then this one, the same thing. Okay, so that's the idea of a limit point. So the idea of a limit point is something's a limit point if it could be the limit of a sequence, not including itself. So we don't include the constant sequence. So it's a limit point if we can arrange a sequence to get there, never touching itself. Okay. So limit points are important. So what is the connection between closure and limit points? Then the closure of A is equal to A union with the limit points. So a limit point may or may not be in A, but it is in the closure. So let's go ahead and prove that. Example. So at the moment, I'm sort of concentrating on R just so you get a bit of intuition. But then later, I'll pull the rug a little bit under you and see that in perverse topologies, it might not act like R. In R, in the standard topology, it's actually very straightforward, right? Because you've got a distance. And a distance makes life easy for you. You can have topologies without a distance. And then you've got to think a little bit. Okay, so we want to show that two sets are equal. So let's show that let's show inclusion one way. Okay. So if X is in the closure of A, so by definition, limit points are included in the closure, and this, and we have that A is included in there as well. So what have I done here? Which? something's in. So this is by 17.5. X is in a closure. Hang on, I kind of lost myself here. If x is a limit point, then every neighborhood of x intersects A. So by 17.5, x belongs to the closure. Oh, okay. That's what I proved. I proved that anything in A union the limit points is in the closure. Now I want to do it the other way around. The closure is in that union. So if X is an element of the closure minus A itself, we have every neighborhood U of X intersects A. Because it's in the closure. Since X my notes are terrible here. Since X is not an element of the union of intersections but X is not itself an element of U. And this intersects, U intersects A at a point not equal to X. So X is a limit point.
So every neighborhood of X intersects A, but X is not in A.
So how do I let X be a limit point.
How is X not an element of U?
Hang on. What have I got here? Oh, okay. So first off we want to show that this set is contained in that. So let X be an element of that. Okay. So if X is in A, then we're done. So therefore, we've got to show that if X is an element of the closure without A, then I want to show X is a limit point. So since it's in since it is in the closure, we know that every neighborhood of X intersects A by the definition of closure. Because X isn't in A, U, here we go, that's what I did. Since X is not in A, U intersects A at a point different from X. And that's exactly what we need for a limit point. Okay. Sorry, my notes got screwed up. So a useful corollary of this is that a subset is closed if and only if it contains all its limit points. And that kind of follows straight away. Okay. So we've defined closure and limit points. Now, as I've said before, when we study topology, just the axioms of topology themselves are very weak, and you need stronger other conditions to be able to actually prove things. So if you're studying some problem, you want to use topology, you have like these stratifications of different types of topologies, sort of getting stronger and stronger. Like, so as we've seen before, as I mentioned, R itself with the standard topology, that's quite well studied, and it has lots and lots of, because it has a distance, as well as being a topology, you can prove lots of things about it, like all the standard things about convergence and continuity. And so that's the motivation for defining kind of like sets of spaces where strong conditions hold. So one of the most useful things to do is the idea of convergence. So you've already seen with this in calculus. The whole idea of having a limit gives you lots of really strong mathematical results. So how do we define convergence when we don't have epsilons and deltas? Right, the reason why we had epsilon and deltas is because we have a distance. So here is how we define convergence in general in a topology. So in a topological space, a sequence of points converges to a point X, provided that for each neighborhood of X, there is a positive integer, capital N, such that Xn is in that neighborhood for all n bigger than that capital N. So you kind of see how the connection between this and the idea of convergence you had before. And before it was epsilons and deltas, right? So that given any neighborhood U of X, right? So that's your delta, like around X plus or minus delta. There's a point at which the whole sequence lies within that neighborhood. So we're just saying that's true for any neighborhood. Okay. So a topological space is called Hausdorff if for each pair of disjoint points there exists neighborhoods U1 and U2 of X1 and X2 that are disjoint. And so the old joke is that it's Hausdorff if you can, they're housed off. So the idea, right, you've got 2 points X1 and X2. There exists a U1 and U2. For example, R with the standard topology is definitely Hausdorff, right? Because as long as the points are disjoint, you can get a small enough interval around it. And in the next slide, we'll see that this useful technical detail about having this means that sequences, it prevents sequences that converge to more than one point. Let me show you I mean by that. So if you've got x1 and x2, and there's no disjoint neighborhoods, let's say this is kind of like the smallest neighborhood containing x1, also contains x2, then every sequence that converges to x1 is also going to converge to x2. Right, because if there's no distinct neighborhoods different, then there's nothing stopping it. So a useful thing I can think of is think of the disjoint topology. What are the convergent sequences in the disjoint? The discrete, sorry, what did I say? In the discrete topology, yes. What do sequences look like in the convergent sequences look like in the discrete topology? Right, so remember that in the discrete topology,
every set is open, so
every set is open. So
if you have 2 points, you can put like an open set around both of them. Right?
So, but importantly, there's a neighborhood that consists just of x1.
Right.
So in particular, there has to exist a positive integer n such that xn lies in here for all big N, right? But there's only one point in there.
Oh, so it has to be a constant sequence?
Right, so the only convergent sequences in the discrete topology are eventually constant sequences.
Okay.
Let's think of the other extreme. What do convergent sequences look like in the indiscrete topology, where the only open set is the whole topology itself?
Then every sequence converges to every element of the...
Right. Yeah. So yeah, exactly. Any random sequence is going to define to any random point. Okay. So they're the two extremes. So typically so here is a weaker axiom than the Hausdorff axiom. That's the T1 axiom. The condition that finite point sets are closed is called the T1 axiom. This axiom is weaker than the Hausdorff condition. Let me give, so what's an example of a topology that is T1? So the, what is it, the finite complement topology is T1, but not Hausdorff. Right? Because basically, in the remember the finite complement topology, open sets are ones that the complement is finite. Well, if the complement is finite, that means finite sets are closed. So this is basically the definition of a finite complement topology. So it's T1, but it's not Hausdorff, right? Because what do we need it to be Hausdorff? We need an open set being disjoint. So if you think about it, so let's think of R under the finite complement topology. Let's look at 0 and look at 1. Well, what's an open set containing 0? It's any finite, it's any set containing 0 but just missing a finite number of points. The same for 1, it's missing just a finite number of points. But if these are missing, both missing finite number of points, since the complements are infinite, the intersection can't be disjoint. Okay, so this is an example of something which is T1 but not Hausdorff. So what about sequences in this topology? So let's look at our favorite sequence 1 on n, right? We like 1 on n going to 0. Well, what does it do in the finite? Well, it does go to 0, right? Because every neighborhood containing 0 eventually contains 1 on n for n large enough. But so does 1. Right? Because anything here, any neighborhood of 1 is the whole of R except minus finite number of points. So there is going to be a large, since it's only finite number, it's eventually any sequence is going to include.
So is it still converging to everything?
Still converging to everything.
Okay.
So this is a pretty crappy topology.
Can we have a topology where it's only converted, or the sequence is only converted to a few things rather than everything?
Sure. I mean, like a trivial example is like think of the 3-point topology. Where those are open sets, then a constant sequence converges to that, but any sequence consisting just of these two things it will converge to both things. So yeah, you can have trivial examples like that. So finite sets are also a good source of counterexamples. Okay, so Hausdorff is T1. Why is that? So it suffices to prove that just singletons are closed, right? Because then a finite union of singletons is going to be a finite set. So what are we going to do? Oh, we want to show that Hausdorff is T1. So let X naught, we want to show that this is closed. So let's say we have X naught. Why did I do that? Oh. So let's X naught, and let's have an X1 which is not equal to X naught. Okay, so since it's Hausdorff, there exists open sets U and V disjoint such that X naught is in U and X1 is in V. That's the definition of so X naught is not in V by definition of disjoint. So X1 is not in closure of U. but that's true for any point not equal to x naught. So every point not equal to x1 is not in closure. That set. So this is closed.
Next one is not in the closure.
So hang on. My notes are really crappy this time. X1 is not in the closure of, sorry, should have written X0. So yeah, so since these two sets are disjoint, X0 is not in this set here, so X1 can't be in the closure of X0, but that's true for arbitrary point X1. So
U is the neighborhood of X0.
Yeah.
It doesn't contain X1. So X1 can't be
in the closure of just the point X0. Yeah. This is true for all things. So let X be a space satisfying the T1 axiom, and let A be any subset of X. Then the point X is a limit point of A if and only if every neighborhood of X contains infinitely many points of A. Let's go ahead and do that. So it's an if and only if statement. Let's do one that direction. Let's say every neighborhood of X contains infinitely many points of every neighborhood of X intersects A infinitely many points. So, but that's, if it intersects in infinitely many points, then it trivially has to intersect at one point other than X. So X is a limit point. So that direction was trivial. Let's look at the other direction. So let's say X is a limit point of A, and let's assume, let's do contradiction. Let's assume there's some U, a neighborhood of X, which intersects only finitely many points. let's get a contradiction from that. So U then intersects A minus the point X at finitely many points. So let those points be x1 through xn. So let's set x1 the U intersected A minus the point X. I'm running out of chalk here. Oh, okay, but now we use the fact that we've got the T1 axiom. So we look at X minus those collection of points. And what can we say about this set in a T1 axiom?
That's closed.
So this is closed, so this is open. But if we intersect this with U, this is open, and it's a neighborhood of X. And it doesn't intersect by the way we set it up. It doesn't intersect with A minus X. And so that tells us that X is a limit point. There's a contradiction right here. Okay, so the nice thing about a Hausdorff space is that's what you need to get rid of the nasty thing about where you've got a sequence converging to more than one point. Why? T1 didn't do it, but Hausdorff does. Why is that? So let's say we have xn going to x. Oh, so this is some definition here. So if we say that if we have a sequence which converges to a point x, then we just write this as per usual, and we call x the limit of that sequence. So the whole idea of a limit makes sense in Hausdorff spaces where it doesn't really in non-Hausdorff spaces. So let y be another point not equal to x. So since it's Hausdorff, then x belongs to some u and y belongs to some v. So u, v disjoint open sets. But we've got that xn goes to x. So what does that mean? So that means that there has to be infinitely many points of the sequence in U. So at some point, the tail of the sequence lies entirely in U. Therefore, it can't lie in V. So Y So xn cannot go to y if x is equal to y. How are we going for time, by the way? Oh, okay. So the last thing that I wanted to talk about with Hausdorff spaces is that things are, so like a product of Hausdorff spaces is Hausdorff, a subspace of a Hausdorff space is Hausdorff, and that works pretty trivially, right? Because if x cross y is an element of a product of Hausdorff spaces, then what have we got? So if we've got x cross y and we've got a cross b not equal to it, then if a doesn't equal x and b doesn't equal y, then we have spaces, we have neighborhoods of A, U cross B, and here we have W cross Z, right, which are disjoint. But one of them is allowed to, because then, okay, we still got at least one of the subspaces has to be equal. So as long if they're disjoint here, then they're going to be so U cross W and U cross Z are going to be disjoint if W and Z are going to be disjoint. And the same thing trivially is true that a subspace of a Hausdorff space is Hausdorff because we have neighborhoods which are disjoint, and if we intersect them with the subspace, they're still going to be disjoint. So let's, for the last thing, let's show that every ordered set is a Hausdorff space. Okay, so let's say we have x and y. What have we got to show? Got to show that there's disjoint intervals, right? Okay, so we've got to trouble. Like if there's something between x and y, let's call this A, and if there's something less than x, let's call it A2, and something greater than y. So since it's an ordered space, we can say with that generality that x is less than y. Okay? So if this is the case, then we can have, look at A2, A1, and A1, A3, and they're going to be disjoint. Okay, so the only thing that goes wrong if we're missing these guys here. Okay, so what happens if we're missing A3? Then Y is the largest element, and then A1, Y works. What happens if we're missing A2? Well, then the same thing, A2, A1. Or what happens if we're missing something there?
Or you can use, like, just use the other one.
Exactly.
And open ring point. So like, the closed on X and open on Y, now it's between X and Y.
Exactly. So you just go through every case.
Did we require that we had at least 2 elements in order to find here?
Yes.
Okay, that's good.
Right. And so, yes. Although I guess if there's just one element, then is it trivially?
Make an order on one element.
It's, I guess, the trivial order. But I guess it's also trivially Hausdorff because, yeah, I don't know, whatever. But yeah, okay. So, and that's kind of what you expect. So, ordered sets give you nice topologies. So they're Hausdorff, so that shows you that it's nice. And then products and subspaces behave as we expect. Okay, that finishes that section.